I do hope you're not too sleepy yet, so I will try to speak very fast. For one thing, because there's too much stuff to talk about, and for second thing, I do want to talk to you guys more personally if you have any questions or something. So, actually I can go further away. So, the talk is titled Reactive Streams, Akka Streams, and how it changes the ecosystem of the JVM. What I mean by that should be clear in the first 5 slides or so, which is that Reactive Streams are up to for inclusion in JDK 9, and it's been a collaborative effort we're all really proud of. And yeah, there's going to be lots of details about that. So that's me. I work on the Akka team in Europe, so which is why I'm really, well, not that really, but really in the US. Also, I run a conference, so if you want to visit Poland, this is a great conference you can visit, and we try to help out speakers with their travel budget. So let me know. Okay, Akka in random projects, like companies, but one thing I do want to know is who's actually using Scala in some way or another, and same question for Akka, like one way or another using it. Okay, that's great. Okay, so we don't have to talk too much about Akka itself, and we can focus on the meat today, which I think is great. So that's the plan. A little bit of story. Then we're going to talk about the Reactive Streams protocol, and that's an important word there. It's a protocol. It's not only these 4 interfaces. It's actually, these 4 interfaces and how they talk to each other, right? So it's a concurrency protocol. And then our implementations, so Akka Streams and Akka HTTP built on top of that. And I want to show you guys a demo what it actually does, right? Because this is the important bit. Okay, very, very short story. So reactive extensions, 2009, I believe, first introduced in .NET. Of course, not the first appearance of functional reactive programming, but one of the first inclusions in a major runtime of that style of programming. So that's 2009, and that was mostly targeted for UI development, right? It was for I'm clicking the button, and I'm getting a stream of clicky events, and I'm doing the clicky sound or something like that. And that was by Eric Meyer, right? So fast forward 2013, we're also pushing for the reactive kind of programming style, and our tools, so Play and Akka, and then again I'm getting lots of feedback here, so sorry. Okay, now it's better. And then Akka Play and RxJava. So all of them already around in 2013. RxJava was just starting in 2013, early 2013, I believe. And they all kind of tackled similar things, but from different aspects. So for Play it is cracking up a little bit, isn't it? Or only for me? Okay, sorry. So for Play it was basically, okay, we need this pull-based backpressure thing. So they stole an idea from Haskell, which is enumeratees and iteratees. And it's a nice functional concept that you can use to express pulling data from this enumeratee, which is iteratively, well, enumerating the incoming data stream. The problem about it was it's not very nice, as in a little bit too complex. Like, just by looking at this API, are you sure how to implement it? Well, not really. So that was the problem with iteratees and enumeratees. We do solve the problem, but they're a little bit hard to, well, a bit too hard for daily use and implementing them ad hoc all the time. So in Akka, we faced a similar problem. We do need backpressure, but we faced it on a very low level. So we specifically talk about sockets and how we write data to sockets and read data from sockets. And there we solved it with negative acknowledgements, and we'll talk about that in a second. So we had that solved in another way, but it was not a very high-level API. So it talks specifically about bytes, nothing else. And then Rx had another part of it solved, which was the nice API part of it. It had no concept about backpressure at all, so it was more focusing on the nice, fluent APIs, right? So when you look at this chart, you'll probably realize, well, everybody kind of has a part of what we need, so why not combine them together, and then we'll get something that's actually really useful, which is what we did. So all these people banded together. around 2013, October, Roland first meets with Eric Myers over .NET implementation. During the recording of reactive programming, principles of reactive programming, you may have seen on Coursera, this massive online course. So they meet and get chatting about it. And soon after, Victor meets here in San Francisco with Ben and other guys like Marius and Eric. And the term reactive non-blocking asynchronous back pressure gets coined. And this may sound a bit too long, but it's actually really important. Each of these words has a meaning in this definition that we're going to talk about. There's going to be a picture, I guess. Hello. Okay. Okay. So the goal is perfect timing. So the goal is there's this fuzzy definition here. What it means is this. So it has to be asynchronous because we basically want to solve back pressure over asynchronous boundaries. That's what we're solving. Why is it not for synchronous boundaries? Because for synchronous boundaries, it's a no-brainer. I mean, I call the method, and I don't do anything until it returns. That's back pressure, right? Boring. We want the same thing, but in an asynchronous context, right? Why do I want to be asynchronous? Because I want to not block, because I don't want to waste threads, right? You guys know Akka, you know why we're doing that. I don't want to waste resources. So, we want it to be safe, so we don't want to cause any buffers for to overflow and stuff like that, right? So that's the back pressure part of it. And then it was a decision to make it a purely local abstraction, and I'll explain how we go into the distributed setting, even though this is a local abstraction, right? So don't ask questions about message loss when I will be drawing messages here, because when it fails, the entire thing fails, right? It's not a distributed system in the examples I'm going to show. And yeah, it should allow synchronous implementations. So while it's focused on asynchrony, it must not, be strict enough to not allow synchronous implementations. Why do we want that? Well, because some very specific streams, it just doesn't make any sense to spin up a thread if I will be emitting nothing, right? My stream is empty, so why would I even start my asynchronous pipeline if I'm about to do nothing? Or just one element or something like that, right? So it's for optimizations. It must allow synchronous versions as well. And yeah, for our examples today, it is compatible with TCP. It's not competing with TCP, which was a misconception that I had when I was doing this talk yesterday at LinkedIn. All the questions were about, why don't you use TCP? It's not competing with TCP, it's working with TCP. Okay, so then we pull in the pivotal guys, which is where the moment this idea starts to be not only, let's write an API for us. Here is the moment when we start thinking about, let's make an API, and we see lots of people have the same problem. So since we're about to solve the problem for more than one implementation already, how about we solve it in a way that solves it, for everybody? And then we can use it for interop between libraries, right? So I don't lock you into Akka, and you can just interop Akka with Rx or Pivotal's implementation. Nice thing to do. So this is where Reactive Streams come up, and Doug Lee, so that's the person basically behind all of the Java concurrency classes, joined the efforts. And Andre from the Akka team, and Johannes and Matthias from the Spray team, and many others joined the efforts. And a year of discussion later, we finally have something to ship. Somewhere along these times I join, and I end up writing most of the TCK, so the Technology Compatibility Kit. This is actually really important because we want to have multiple implementations, but they need to do the right thing, right? So we need some kind of test suite that's testing all the weird racy conditions, because this is a concurrency kind of protocol, and we want to make sure if you're passing the TCK, I can trust you that I can use your library and it's not obviously wrong, at least. It may be weirdly wrong, but at least it's not obviously wrong. So April finally wanted 0 release, which is why the title, The Rise of 1.0s, because afterwards lots of libraries release their 1.0 releases being compatible with this as the underneath interfaces. So this is only 4 interfaces: publisher, subscriber, subscription, and processor, which you'll see in a moment. And the most exciting thing about this story is the JEP 266, which is the inclusion of these interfaces in the JDK 9. this is already merged. Here's the link to the commit which merges this into the JDK, so it's up for inclusion. And like I said, it's this cumulative effort of everybody involved. So not only us. Everybody saw the value of it, kind of. Okay, Akka, you guys know what Akka is. Concurrent, distributed, asynchronous. Next. So, why do I want back pressure? Let's say you have your car or system, and you want to avoid this. Right? So this is a system without back pressure. It's overflowing buffers and it's crashing. So yeah, our motto is let it crash, but not in that sense. It's let it crash and then, you know, recover gracefully, right? That's not gracefully, in case you're thinking. Okay, so what is back pressure? It's not back pain. It's not back pain, but it's back pressure is needed when you have this this situation. So we have a fast publisher of data, slow subscriber of data. And yeah, these are the words used in the spec, and this is not PubSub. Another misconception, initially, since we talk about history, these were called producer and consumer, etc. And a multiple number of renames after, we stuck with publisher and subscriber. And now on every presentation someone asks, is this PubSub? No, it's not PubSub. It's a strictly one-to-one protocol. So we have a fast subscriber and fast publisher and slow subscriber. And we have some kind of messages. Let's first talk about the possible solutions to the back pressure solution, to the back pressure problem. First up, the negative acknowledgement, which we have had in Akka.io, right? The writing to TCP module. And it's also expressed as in messages. So eventually there's going to be some kind of buffer on the receiving end.
What's negative acknowledgement?
I'm about to explain. So negative acknowledgement, what is it? It's exactly what I'm going to explain in the next 3 slides. So you have this buffer, and even if you think you don't have a buffer, you have a buffer. Let's say you have a thread pool, and you're submitting stuff to the thread pool. Stuff is queuing up in the threads pool submission queue. You have a queue. If you're sending data to, I don't know, TCP, UDP, whatever, there is the operating system's write buffer. There's always some kind of buffer. Maybe you're not aware of it, but there is a buffer. So in our case, it's an explicit buffer for a certain number of envelopes. And when that grows out of bounds, then, well, what happens? A number of things can happen. So what usually happens in most distributed systems, at least the well-designed ones, is dropping messages and then requiring resends, right? So we don't blow up, but we require the publisher to resend the data. This is what TCP does, right? Easy. So what else can we do? So you can add more memory, right? You can try to add more memory, but that doesn't scale infinitely, and then you're out of memory, so which is not a viable solution to our problem. But a possible solution is negative acknowledgement, which is exactly that. So I'm looking at my buffer, and I'm consuming from my queue at 1 operation per second, but this guy is still faster. So I notice, I'm about to run out of buffer space, and I will try to notify the publisher that, hey, would you slow down a bit? Or, you know, I can't keep up, would you stop sending data? Something like that. But the problem is, since this is an asynchronous system, this may not make it in time, right? Because the messages which would overflow my buffer were already in flight. So it's not really helping the correctness case, while, well, maybe often it would work, but not always, right? So not a good thing. Actually, the reason why we had it as a negative acknowledgement is this is what the operating system gives you. When you write to a socket, the socket can say, well, I didn't manage to write, I have my buffer full. But in the operating system's case, that's a synchronous API. So you can keep spinning on the write until it succeeded. But in asynchronous systems, yeah, sadly it doesn't work as good. So this doesn't work. And then we have the other case where the subscriber is faster than the publisher. And there exists a theoretical third case where they have the exact same speed. However, in reality, yeah, it doesn't really happen. They always oscillate a little bit, right? Even if they're mostly fast, exactly the same speed, they always oscillate a little bit. Okay, so what do we want? We want So just pull would be too slow. Pull means give me a message, and I get a message, give me a message, I get a message. But that's, you know, doubling the number of messages we send over the wire or over threads. So we don't want to do that. We need to switch modes. But whenever we would have something that switches modes, there's this one point in time that is this switch mode point in time, which is, again, unsafe. So we don't want to switch modes, but we do need two of them. So how do we do that? We have one mode which basically expresses both of them in the same protocol, which is this. So instead of asking for a message, we can ask for 3 messages because we know I have space for 3 messages, right? In an abstract manner, we can think of it this way. So if the publisher got a notification that, okay, I got request 3, which means I can send up to 3 messages, and whenever I send a message, I will decrement this counter. And I'm not allowed to send more than the downstream has signaled demand for, okay? So this is kind of like pull, because this guy is slower, so he will be slow to sending these requests. However, he can send this as one combined message. It doesn't have to be always by one. Right? So he can send a bigger number. And if the downstream is faster than the upstream, then he will always send, bigger numbers, which effectively means this guy can go as fast as he possibly can, because he'll never overwhelm the downstream. Right? Because there is buffer space ready for the messages which will be coming in. So we're both safe and we can optimize this. So that's the protocol. There's other optimizations like the publisher can accumulate this demand signal, right? By obvious summing of demand numbers, easy. And then he signals the messages. So, like I said, the goal was to not only make this solve our problem, but also solve the interop problem. And I'm happy to say that we have like 5 or 6 or 7 by now implementations that are actually using this, and you can use it for interop. So this is one thing I want to tell you guys. So this is not a nice API to implement because of all of the weird race conditions between arrival of subscription and demand, etc. However, you can certainly do it. I won't forbid you guys. However, it's not the go-to solution. You shouldn't, first thing I want to do, if I need back pressure, you shouldn't implement this thing yourself, just use an existing implementation. Don't waste efforts. We've been writing this for a year, still got bugs sometimes. So don't waste your time, just use an existing implementation, and which looks like that. So I hope you guys are familiar with at least Rx. So observable of a number of ints, and then so in Rx they couldn't really change their APIs because it would break existing clients, which is why currently they have this bridge method. It's a to publisher, but in the 2.0 release it will implement it directly, right? So in our implementation, you can get a source from an int publisher, and then you can just run to a fanode publisher, etc., etc. And you can see, using this interface, all of these different implementations abides to the same protocol, and the back pressure works all the way down from this guy who's actually writing to the socket to this guy who's generating the data. So that's a pretty boring source because, well, this is not gonna overwhelm me because it's an iterator and I just pull from the iterator. But it's interesting in hot sources, right? These clicky streams, or if I want to not read from the database because something, or I want to collapse data from a click stream, stuff like that. So finally, Akka Streams. So what is it about? It's one of the implementations of this protocol. We've been driving it from the beginning. And we're pretty happy with the result, let me say. And it's been rewritten like 6 times, and I just don't want to rewrite it anymore, so I'm happy that we're happy with the current implementation. But I don't want to talk too much about Akka Streams because it basically looks like Scala collections, with one difference being that it's a fully lifted representation, which means when you write, for example, source, map, filter, something, this is basically an AST, right? So it's a abstract. It's like a graph which contains the information what we're going to run, And it's completely detached from the execution engine, which means that we can materialize in a matter of different ways, which allows us to do different optimizations before we run the thing. So this is, I think, the biggest differentiator from all the other implementations, and we can't really do as sophisticated optimizations as we can thanks to this lifted representation thing. There is a startup cost, but we can always cache it. And then the actual interesting application of this is our HTTP pipeline, which is basically Spray 2.0. If you've seen Spray, nice HTTP library, and Spray has basically become Akka HTTP, with all the internals being rewritten and reshaped to use streaming. The effort was basically the last 1.5 years, or maybe more, with the Spray team and us working together on that. So, how does it look like in 20 seconds? Well, pretty much like a Scala collection, right? First some maps, first group, and all the usual operations. But the interesting part I want to show you is, so you have some kind of source, and you have some kind of sink, and yeah, we finally have proper typing in Akka. Woohoo! And there is a flow. So flow is something from input to output, so like a function. But it can do a bit more than that, and it also internally implements the Reactive Stream interface on both sides. So a flow is both a publisher and a subscriber, right? Because it's a subscriber from this side, right? It's getting data, but for this side, it's a publisher because it's emitting the transformed data, right? And those, in the spec at least, are referred to as processors and are a nightmare to implement correctly, which is why I ask you to not try to implement them like by hand. But if you do, at least use the TCK, then at least you're gonna see what kind of mistakes you can make. I'm not saying you will make all of them, but certainly some. Okay, so a recap, basically source, one output port, flow, one input, one output, sink, one input. So this is the corresponding wording we use in Akka Streams to describe the corresponding Reactive Streams interfaces. And like I said, because the Reactive Streams interfaces are not intended for user land anyway, this is a good thing. So you're hidden from accidentally trying to implement, the low-level thing. But if you want to, you can get a publisher out of it, right? And there is a power mode. So power mode is a flow graph, which can have an arbitrary number of ports incoming and outgoing. Typical example would be, nice tweet. Typical example would be some kind of, let's say I'm a merge of data, so I'm merging a stream of some statistics with a stream of what page the guy was and what page this stats were collected from, and then I'm emitting, well, maybe some collapsed statistics, but also maybe a total count of views on this page up until now, stuff like that. You can imagine arbitrary complex graphs. And also each of these is actually a flow graph, but internally it's very simply a flow graph with one input port, for example. So it's very consistent in terms of API design. You just learn these concepts and it all fits together. So yeah, it's a implementation of a HTTP server. It's not only a routing DSL, it's not only an MVC thing, it's the entire stack, right? From reading from TCP, from writing to TCP, through the routing layer, through the actual marshalling infrastructure of how do I take my object into a protobuf or JSON thingy, right? So, and it's buffers over way down, which I want to show you guys in an example. So, obvious example for any kind of streaming APIs is something that has an infinite stream of stuffs, for example, birds or tweets, how people call them. So you have this source of tweets, and it's hot, right? The tweets are coming in, and I need to push them to the client. I'm doing some transformations to the tweets because, I don't know, maybe I'm filtering them, maybe easiest thing to do is transform that to JSON, right? And then I'm writing to TCP. So up until now, this is Akka HTTP. Well, Akka HTTP also has the TCP implementation, of course, right? But then there's the operating system layer. And like I said, there's buffers all the way down. So each of these stages has a buffer. And then we have a send buffer and a receive buffer on the operating system level. And well, when we try to stuff stuff in to the send buffer, the operating system can say no, because it's full. Then this stage will stop writing, by which I mean it will stop signaling demand. Right? Then this stage will fill its buffer and will stop signaling demand, which will stop signaling demand to the source, which will make the source stop signaling tweets. Okay? And the stop signaling tweets can be interpreted in multiple ways, right? So if it's a source that you can actually stop, then it just stops generating the data. Like if you're reading from a database or something, or from Kafka, right? But if it's a source that you cannot stop, then maybe you can start conflating the numbers or dropping some of the messages or doing stuff about it, but it's your conscious choice, right? And I'll show you how to do that. Okay, so data flows here, and opposite to the direction of data flow, the demand flow is going. And that's managed for you by this underlying reactive streams layer, right? You don't need to care on the user level APIs about demand. It's good to understand why my flow has stopped working, right? Maybe it's the right thing that it stopped working, right? Okay, so no demand from TCP, no demand to upstreams, doesn't generate tweets, which means bounded memory stream processing, which is the goal we want to achieve here, because when you see a pipeline, you know, okay, here I have this much space for buffer space, here I have this much buffer space, and you exactly know how much at most memory will be used for a guy streaming the tweets, guy or girl streaming the tweets, which is a pretty cool thing to do, because in other tools, well, do you really know how much buffer space the entire thing will take? Will it even buffer? What happens in a usual MVC thing? So, demo time. I want to show you guys how this actually works with showing the actual operating system buffers. Too much stuff. Okay.
What do you need IntelliJ AAP for? You use early access?
Yeah, to complain about bugs early.
Right.
I mean, why not? Okay, so Akka HTTP, do I need to explain the APIs? Has anyone, if you have not seen Spray or Akka HTTP before, raise your hand. Okay, so a very quick tour of it. So the way you write a Spray application is, well, and Akka HTTP application, because this level of API is pretty much the same, just all the internals have changed, is like that. You have this routing DSL, which means, yeah, there's a path, and complete it with something. So this is not async yet, right? But it could be a future. Right? So this will complete this request when this future has completed, right? Now we have some asynchronous processing. But this is not not everything, because we also have a random tweet source, which is a source of tweet. Oh, and I'll explain the second parameter maybe right now. So the second parameter is a bit maybe surprising, because when you look at collection APIs, well, what is the type of list, right? There's a list of T, it's a list of T's, right? So what is here? It's a source of tweet and something, right? It's a source of tweets, correct. And the second thing is what we call a materialized value. And what this is, we've played around with a number of ways to do the same thing, and we found that this is the most both type safe and understandable once you get the idea. And the idea is, once I run the stream, so this is still a just representation thereof. I told you about the AST. It's not running yet. So, but once I run it, I maybe need to get something back from the stream with which I can either interact with it or inspect it. For example, it could have a side channel, which is a counter which I can inspect, which always has how many elements have flown through this source, right? or maybe it's a control element, right? So it materializes a cancelable. A cancelable is a bad idea because you'd usually cancel from inside the stream, but maybe it's a throughput tweaking something, right? And you can change the throttling from the outside because of some statistics you gathered from somewhere, and you can tweak it a little bit. So it's a way of materializing something from inside the stream into the outside world. In this case, we really don't care because it's an iterator, so yeah. And we map it to tweets, nothing really fancy here, but the fancy thing is, for one, the reuse of flows. So the reusability of flows is interesting because I have a flow of t, and yeah, I map and print every element and just return it. But yeah, that's pretty boring, right? But the interesting bit is no one has to care how I implemented this guy, right? You can just give people a flow of, I don't know, text to wave, sound wave, and you just agree with someone, I'm going to give you a flow of text to sound wave, and you can just assume it's going to work, right? So it's helping to spread and reuse parts of your API. Here I have another one which does something really bad. Don't do this, right? For people in the back, right? Don't, okay? This is just for the example I'm about to show. So how do I write this thing? Yeah, there's a path, there's a get, so on the path tweets. For all the get requests, I will be doing these random tweets, and I complete it with the tweet's source. How does that actually work? There's a to response marshalable, so yeah, there's implicits involved, and this is our marshalling infrastructure. So the way this works is, if I can find a to response marshaller for a given type, I will just start writing this. So of course, how do I render a infinite stream to a HTTP response? Well, there's a number of different ways I could do it. And maybe I'm not going to go into the implementations, but I can show you a little bit. So the spray.json support and the spray.json entity streaming support, which basically means there's the framing. Yeah, maybe I'm not going to dive into all of it, but basically what it is, when I have a JSON marshaller in scope, which I have because I have both a tweet format, which is spray.json for I have a tweet and I want JSON out of it, right? So we have a way to marshal one tweet, and then we have a way to marshal a stream of tweet, which is, in our case, specifically for JSON. And then you can have different modes of how you want to stream it, right? Is it an array? So is it starting with a bracket, or is it just new line separated ones, etc., etc.? Default one is just an implicit that provides write each of these elements in one line, and then a new line, and then the next line is the new element of the stream. So basically a Twitter streaming. And I want to show you how this works. Unless you have questions, you can interrupt me. And this will be probably too low, so I'll higher it a little bit. And yeah, server demo. And on the right-hand side, can you guys see? Can you see that? That's netstat -p -n -p TCP, wrapping on localhost and port 8080. Which means I want to look at the TCP buffers of, this connection. And this is on a watch. And we have a server running. And now I'm going to curl with a client. You don't see that, right? Is that better? Okay. So I'm just curling this guy. And it's generating some tweets. And here we have the writing side, I believe, and here the reading side, right? So if you're just a host with a server, you would have one of these lines. But I have both a sender of the data and a receiver of the data. And now what I'm going to show you is what happens if I interrupt the curl. So I don't control C it, I control Z it, okay? So it's sleeping. And first the receive buffer got full, then the write buffer of the server got full, and then eventually it stopped generating the tweets. What will happen if I resume? Well, first I'm draining the receive buffer, then it drained the send buffer on the server side, because TCP figured out, okay, now you can write data again, and then it resumed. And of course, the last feature here is idle detection, because when can this happen? This can happen if you have a mobile client and someone rides a car and he's suddenly in a tunnel or something, right? He just stops reading the data. And then you want to stop, you have something a little bit buffered in memory at this point. You don't have all the tweets being buffered, but you have something buffered. So I do want to time out if nothing is happening on the connection for a while. So usual idle timeouts, which will time out in a few seconds. I think the default is a minute, so. Yeah, I'll just come back to it when it times out. Okay, so that's one thing. So that's the server writing stuff part. Then we have the server reading stuff part in the same scenario, right? Someone is sending me a very big file, but I don't want to store the file and then start working on it. I want to start working on the being uploaded file while it's being uploaded. And maybe after 5 lines I detect, well, this is gibberish and I just want to abort the connection, right? So this is this guy. So if it's a post request, I want the entity to be a stream of tweet. And again, the same configuration applies. You need to provide an implicit which says, is it a line by line, or is it, I don't know, is it XML, is it whatnot? We didn't implement anything other than JSON for now, but you can imagine any kind of representation of infinite list. You can do your own, like CSV, right? And then you get back a source of tweet. And in this example, I'm waiting for, I get the tweets, and I consume them very slowly, and I count them. But let's also just take 3, and yeah, don't wait. And take 3 means I will take 3 elements and then cancel the stream. Canceling the stream means aborting the connection. Easy, right? And then I complete with a future, with this future. Because this is tweets, and run fold means run the stream and fold it. So this is a terminal operation. This returns a future of result. So once the stream completes, I will get back the sum of how many elements I've got. Then I transform it to a string and just return it. And this, of course, adds all the headers like, oh, it's a string, so it's probably a text plain, UTF-8, etc., etc. So let's see that one. Oh yeah, and now we have a timeout. So the timeout is a very nice track trace. But yeah, it says no elements passed in the last minute, so aborted connection. And I do want to improve that error message a little bit. Currently it's not that obvious, but it's a idle timeout. So now same server, but I want to upload some tweets. How do I do that? curl -d, some file with tweets. That's the typical 1 line per tweet format. And then it's a post, and this is an interesting feature. So I told you guys that this unmarshalling is provided as implicit, but maybe you can accept both JSON and CSV or something, right? So then you provide 2 implicits, and what the marshaller, unmarshaller can say is what content type it understands, right? So we can provide multiple unmarshallers, and then once the request comes in, we look at it, we look at the content type, look at the available unmarshallers, and we try to match one which is able to handle the data. And if we don't, then we reject the request with saying, well, we only handle JSON or text, right? So we do that for you. You don't have to implement any logic for that. Okay, so I'm streaming the upload. And something's wrong. Was it not localhost? Will it be happier with 1.7001 or? Yeah, the demo gods don't like me. It's not actually sending the data, is it? Yeah, demo fail. If it would have worked, would be great. I'm not gonna start debugging on stage. It's probably some silly mistake, and I actually did not run this example yesterday. And I was thinking it would have worked yesterday, and yeah, guess it didn't. So, without further ado, I'll go back to the last few slides. It's 5 or so. Unless you have questions. Why didn't it work? I don't know. Yes.
Put this up on GitHub?
Yes, I will put this up on GitHub, and it will be, of course, in the Akka documentation. This is actually not a merged pull request yet, so which is why maybe it's working.
Where do you control, like, in the beginning, like in the example, say, you know, I'm going to accept 3 at a time, or I'm going to deliver?
Yeah, exactly. How is that? Because we didn't see anything like that in the APIs, right? So what happens is when you have this stream, like I have a source, I have a flow, basically we have a default buffer size, that we just more or less arbitrarily picked. I think 16 elements or so. But you can configure that explicitly by saying with attributes buffer size, and then you save the buffer size. And internally we have request strategies. The default one being if the buffer goes below half of maximum capacity, we request, for this half of elements. So because we don't want to send always request 2, we want to say request 20 maybe.
Yeah, because I was wondering if that could be dynamically adjusted, because that would be the optimal thing to max the throughput.
Yeah. So and if you really know what you're doing, you can go one level deeper, but not fully Reactive Streams deep, but Akka Streams actor publisher deep, so which is kind of in the middle. We do a lot of we help you around to implement this guy, but we do demand management, etc. for you, but you give us a demand strategy. So it's 1-for-1, or you can basically do arbitrary code and decide when you request. So you can do that. You have full control if you want to. So another example was about Pancakes. It's in the documentation. And it's about pipelining. So pipelining is because these two, I'm trying to make pancakes, and I make one side of a pancake on this thing, and another side of a pancake on this thing, and they can go at the same time, and even if their rate is not exactly the same, they can go both fast, and they can even out at a more or less stable rate, because they have buffers between them. So I'm getting out a stream of pancake. This is how it looks. Flow, via one flow, via another flow. And yeah, don't want to keep you guys too long today, so next one, which is parallelism. So I want the 2 pancakes being cooked at the same time, which I can very easily express, inside of a flow. Again, someone is giving me a pancake flow. I really don't care how he's doing the pancakes, I just want my pancakes. But inside, she did something really smart, and actually has 2, how do you call those? Pans, yeah, thank you. You have 2 pans, and you're doing the pancakes in parallel. But from the outside, no one really cares. They're just happy that the pancakes are going out faster.
What is the third type with the underscore?
That's the materialized value, so it could give you a pancake counter or something like that. Additional metadata or additional stuff that the stream can give you back. Okay. So this is how it looks like. This is a slightly more complex API. This is what I called the power user mode. And we're actually trying to simplify this currently. But basically the goal is here the goal here is for this line to look as if you would draw it on a whiteboard, right? So versus dispatch better, output, it goes into something, and then it goes into something else. So it's like having a graph drawn out on a whiteboard, and then you connect the dots. That's the idea behind this API. For this very simple one, you can just use a map async, which starts these 2 functions at most 2 at the same time, and they return futures, right? So same thing, but in parallel. So yeah, use these things, but no one has to actually see them. Right? That's the feature. that you can have it inside, but no one has to care. And yeah, the last thing, we finally have WebSockets after 3 years of waiting. And what is a WebSocket? And it had almost 100 upvotes, and no one would pull request it. So I don't know. Maybe it's a hard feature. It actually is. So what is a WebSocket? A WebSocket is a flow from a message to a message. So handle WebSocket messages. Boom, done. If the upgrade doesn't go through, if it's not a upgrade to WebSocket request, then we just reject this, and it would, handle something else here. There's a tilde, and then you can say complete. Well, I only handle WebSockets, stuff like that. So, interesting thing. How do I do a WebSocket that's only writing data, and I want to ignore, anything the user sends me? I don't care. I'm just a stock ticker. So you do that by combining a flow from a sink and a source. So sink ignore, source single, or source stock exchange. But it looks like a flow because it has one input and one output, right? So stuff like that. Summing up, buffers are everywhere, and yeah, we can sometimes try to ignore them, but it's not really a reasonable thing to do for an engineer, so let's acknowledge them. And this is a good example from the Twitter streaming API. They actually notify you by their state of the buffer, right? Basically, if you're falling behind, like being very slow, they need to buffer on the server side, and they notify you about that, right? There's a falling behind warning, and yeah, it's 60% full. If you continue being slow, we'll just stop serving you the stream, right? So doing stuff like that in Akka Streams, also 2-3 lines, I guess. So soon it's going to be merged. Merged it is, but released, I hope. That's a hope. And I'm not working at Oracle, so I don't have to do this horrible slide with the safe harbor thing, right? Yeah, so don't believe anything I say. I'm just an engineer. So, roadmap 1.1 being released soon in a number of weeks. It's mostly containing a lot of API improvements and a lot of performance improvements. So it's not as fast as it can currently. That's a 1.1. 1.1 milestone 1 coming out this Friday. So it's, a preview. And after 1.1, we're going to merge it to Akka 2.4, but it's still an experimental module. Does experimental mean it's of bad quality? No, it means some parts of the API may still change a little bit. So the usual binary compatibility guarantee that we have on all our APIs doesn't hold yet, because it's still a rather new module. But other than that, you can try it out and see if it works for you. Yeah, I had some roadmap things, some links. Thank you very much. I hope it didn't take too long, because last time I went far over time. Shall we do 1 or 2 questions, and then everybody's free?
Yeah.
Okay, 2 questions. No questions?
Do you know of any big user already of the API?
Yeah, I save it with a psych because we've been telling people to not use it because it wasn't ready yet. I don't know the names actually. But yeah, some smaller-ish companies with not high throughput things have already been using it since early 0.6 previews, and it works for them. But the APIs have changed, like, 6 rewrites. But they're still happy and have been migrating. So, yeah, now it's the time to start looking at it because we're in the performance tuning phase of it, right? And when you're writing an HTTP server, it should be not slow, right? Last one, please.
So you're doing it across machines, like through the TCP?
Correct, it propagates through TCP.
If like on the other side, that means subscriber, I say I'm just going to get 6 at a time, but the producer side, okay, you understand that, but you can't really account for the network latency. And,
no.
And then, I thought I would get 6 at a time, but the rate that it came, because of network latency or bursts and spurts of that, it's going to fall apart because.
Yeah, so the question is, we're kind of doing it across machines because we're talking over TCP, right? And TCP has the windowing mechanism and it propagates the same backpressure that we have in process, but with between threads. Does it fall apart? Because here we're talking, you know, guessing how many requests per second. The current answer is, for current solutions, it's good enough, I believe, because the current cases where we want to use it is exactly the streaming API case. So if people are falling behind, I want to, you know, slow down because there's no reason for me to go full speed. And yeah, some of the lessons that we've learned in this endeavor have been already fed back into Spark, actually. I don't know how early you guys have jumped on the Spark hype, let's put it this way, but earlier it was not that good at not killing itself by overloading some of the, how do they call them? Ingesters? Not ingesters. I'm bad with their naming. The nodes that get the data from, you know, the most outside processes. And they were not really good at, you know, relaying any kind of information from the downstreams to themselves that, you know, no one is keeping up, and they would kill their own nodes. So while it's not directly the Reactive Streams protocol, certainly lessons from implementing this have been fed back to Spark already, and in the last release, I'm bad with the versioning numbers again, but in the last 2.x release that happened, actually our engineers from our Spark team have been helping them out to implement backpressure support in their existing infrastructure. It's not directly Reactive Streams between the nodes, but in process it is. So yeah, it's still an open question how we're going to go about, in the long run, about inter-node communication. And the interesting bit about it, since this is a flow control protocol, we could try to ditch TCP. Now the question is, should we ditch TCP? Because it's, you know, pretty mature and being optimized since 20, 30, 40, I don't know, years, right? But it's an open question. One thing on the table is Aaron. It's a protocol, the same layer as TCP, RARON. It's a protocol designed by Martin Thompson and Todd Montgomery. It's the JVM's high performance guys, basically. And they're claiming that for small messages, so not really for stuff like here, but for small messages, they have really nice throughput, like many millions of elements. And yeah, maybe that's an interesting thing to look at. We have not yet, but these are open roads. So no roadmap updates in that respect yet. And yeah, ditching TCP, tricky question, right? It's very, very good at what it does. So thank you very much, and yeah, thank you.